Hello everyone, I hope everyone is safe and doing good. Welcome back to my channel Trick or Treat with Mathematics. So in today's video, we will be seeing rational numbers and their decimal expansions. First of all, you need to know what is a rational number. So what is a rational number? A rational number is a number that can be written in the form of P by Q, where P and Q are integers and Q is not equal to 0. Right, and you can also say that all integers, all fractions, all terminating decimals and all non-terminating recurring decimals, recurring or repeating decimals are the types of rational numbers. Right, because rational numbers, a rational number can be 1. 1 is also a rational number because we'll say 1 by 1. A rational number can be like 2 by 3, 5 by 4, 11 by 13, minus 24 by 25, etc. So all these can be rational numbers. But you also need to understand that rational numbers have the decimal expansions as terminating or non-terminating and recurring. This is what we focus on in our entire video today. We will see how the decimal expansions of these rational numbers can be represented and how we are saying that those expansions are terminating and those expansions are non-terminating but recurring. Okay, so this is a quick overview of a rational number. So any number that can be written or expressed in the form of P by Q is, and where P and Q are integers and Q is not equal to 0, is called a rational number. Okay, so with this knowledge in mind, now let's focus on terminating and non-terminating recurring. You need to understand the definition or the meaning of terminating decimal and non-terminating recurring first before we move forward. So, terminating decimal. I will give you this fraction or rational number 2 by 5. What is the value of 2 by 5 in decimals? Is it not 0.4? Right. What is the value of 1 by 4? It is 0.25. So, these are definite values. What is the value of 1 by 3? 0.333 and so on. Right. What is the value of 2 by 3? 0.666 and so on. The difference between these two set of numbers. That is, here there is no continuity. 0.4 is a definite value. That means it is terminating at one point. The decimal expansion is terminating. Terminating means stop. It is stopping at one point. Here also, if you see 1 by 4, it is stopping after 5. We don't have any value after 0.25 or any digit after the decimal expansion of 1 by 4. It ends only after 2 digits. The decimal expansion of 1 by 4 ends only after 2 digits. How do you say that? If we divide 1 by 4, we get this as 10. 2s are 8, 20, 5s are 20. What are you seeing here? You are seeing here that the decimal expansion ends after 2 digits and the remainder is 0. So whenever the remainder is 0, when you divide two numbers and the decimal expansion stops after a certain step, as soon as the remainder comes as 0, then that is called as terminating decimal. So terminating decimal is nothing but number. If at all, it can be represented in the form of decimal, and if we represent that number in the form of decimal expansion, then if it stops, the decimal expansion stops at a certain point and the remainder is 0 at that point, then we call it as terminating decimal. Okay, now this is clear in here. In the same way, 2 by 5 also 0.4 because it stops at one point. Now let's tackle this situation. What is 1 by 3 here? 1 by 3 we are dividing 3 by 1 again. What are you observing here? There is a repetition of pattern here. And there is no end to this decimal expansion. It keeps on going on. It is not stopping at any point for us to define the value for certain. Right. So can I not write this as 0.3 bar? Here bar represents recurring or repeating. Right. So whenever we divide two numbers and you are representing that fraction or rational number in the form of a decimal expansion, and that decimal expansion is not stopping, or there is no stop to that expansion after a certain point, and if you are seeing that the expansion is repeating, there is a sequence, there is a pattern of repetition of that decimal expansion, then we call them as non-terminating. As the name suggested, it's not stopping at one point, but it is repeating, recurring. Or you can also call recurring as repeating decimal. Okay, so this is actually the meaning of non-terminating recurring and terminating decimals. These two are all rational numbers. Okay, but you might be having a question. What happens if this pattern doesn't repeat? What happens in that case? Can we denote that as a rational number? No, we cannot, because there is no pattern that repeats after a certain time. Let's see now. Pi. There is a value of pi, 3.14 and so on. If you see the clear full expansion of pi, I will be placing that in the screen somewhere. But if you see the clear expansion of pi, there is no pattern or there is no repetition after the dot or after it reaches the decimal position. It keeps on going on forever. Right? And also with E is a constant and it is something of this sort, 2.71 and so on. There is no pattern as such for that. It keeps on going on and there is no end to that number and there is no pattern at all. So in this case, pi and E can be denoted as non-recurring and non-terminating because they are not stopping at one point and they are not repeating as well. Okay, so this is how you represent an irrational number. So as I told you before, irrational numbers are nothing but numbers that cannot be expressed in the form of p by q, and the numbers that has the decimal expansions as non-terminating and non-recurring are called irrational numbers, and pi, e are some examples. Okay. How do you know whether a expansion of a rational number can be terminating or non-terminating recurring? How do you identify that? For example, I will give you this decimal expansion. Okay. Now, I will write this as this. Am I right? This is how I am converting a decimal into a fraction. Now, if you observe the denominator here, 1000, how do you prime factorize 1000? Now let's try to prime factorize it. 2 5s are, again 2 250s are, 5 50s are, 5 10s are, again 2 5s are, right? So what is it? 2 cube into 5 cube. Right. So 1000 can be expressed in the form of 2 cube into 5 cube. Again, let me give you one more example here. I will give you 1.25 or you can say 31.25. How do you write this? 3125 by 100. And what happens if you prime factorize 100 leaving the numerator? You'll get 2 square into 5 square. That is 4 into 25 is 100. What are you seeing in these two numbers here? What is the pattern that you are seeing? You are seeing that the denominator of these two expansions, once you convert them into fractions, is in the form of 2 power of n into 5 power of m. That is, the denominator, if we prime factorize the denominator, then we will get the form of 2 power of m into 5 power of n, where m and n are non-negative integers, 0 and positive integers. Okay, so we have got a conclusion that the denominator is in the form of 2 power of n into 5 power of n, 2 power of m into 5 power of n. Right, here you must be saying that these two are equal. Yes, there are cases where 2 and 5, the powers of 2 and 5 can be equal, can be greater, can be less. But this is how you represent the denominators. We'll see those cases a bit later now. But this is the pattern that you see. So, how do you know, based on this concept, whether a number is terminating or not? You can say that whenever the denominator of a number, if that can be expressed in the form of 2 power of n, m into 5 power of n, only 2 power of m into 5 power of m, or 2 power of n or 5 power of n. If the denominator consists of only these three prime factors after prime factorizing the denominator, if it consists of only these three prime factors, then you can say for a fact that that number is terminating. Okay, the decimal expansion of that number is terminating. If you have anything other than 2 and 5, or if you say, for example, you have prime factors as 2, 5 and 7 also, in that case also it is exceeding two numbers. So it is not exactly these two. The prime factors are not exactly 2 and 5. It's something else, something more. In that case, we will not get a terminating number or terminating decimal expansion. Okay, with this understanding in mind, now let's see a quick theorem based on this. This is a theorem based on whatever concept I have taught you just now. The theorem states that let x be a rational number. Okay, and this rational number's decimal form will terminate. The terminating decimal expansion, and x can be expressed in the form of p by q, where p by q are co-primes. Let's deal with this now. And the prime factorization of q is in the form of 2 power of n into 5 power of n, which we just saw, where m and m are non-negative integers. Now, he is saying that, in short, for example, if we take 0.375 as a number, a decimal number, how do you convert this into fraction? We'll write it as 375 by 1000. Now, concentrate the word coprime here. What is the meaning of coprime? Coprime means nothing but the HCF or GCD of those two numbers is 1. In short, the only common factor that divides those two numbers is 1. Right. I've explained you the concept of coprime in detail in one of my videos that I will link up here. But that is the meaning of coprime, you understand, right? Why is it saying that it should be coprime? Because in order to express this in the form of 2 power of n into 5 power of m, we need to factorize, right? But sometimes what happens is, in this case only, we can divide these numbers, as in these two numbers have other than 1 as a common factor for sure. In this case, you can say 5, 25, etc. are common factors of these two numbers. 125 is also a common factor, right? That means these two numbers have a common factor other than 1. If you take the lowest form of this number, that is, if you take the lowest form of a rational number, the lowest form would be p and q being coprimes. That is, if they don't have other than 1 as a common factor, then after that, if the denominator is in the form of 2 power of n into 5 power of m, then you can say for a fact that the number is terminating. That is what this theorem is all about. Okay, even though if you do not consider co-prime also, what happened I'll show you. We have seen that the prime factorization of 1000 is 2 cube into 5 cube. Right. What is the prime factorization of 375? 375 can be written as 5 7s are 35, 75, 5 15s are 5 3s are. So, can we not write this as 5 cube into 3 by 2 cube into 5 cube? Yes. But if you see here, there is a common factor in numerator and denominator. What is it? 5 cube. So, we can cancel this. Right. And so, what is remaining now? 3 by 2 cube. In this case, what is the form of the denominator? 2 power of n. And if you further write this, it is 3 by 8. Right. The denominator is in the form of 2 cube. That is 2 power of 3. Right. And it is in the form of 2 power of m into 5 power of 0. Right. So, based on this, can we say that this number is a terminating decimal? For sure we can say that, because this number is co-prime and the end result we got is co-prime, and we can say that it is in the form of 2 power of n into 5 power of m. Remember, it should not strictly be in the form of 2 power of m into 5 power of n every time. It can be in the form of 2 power of n only. The denominator can also be in the form of 5 power of n and both. But if there is any prime factor apart from these three possibilities, then it will not be a terminating decimal. Okay. So, this is the concept of terminating decimals and how to determine whether a number is terminating or not. 2 states that when x is p by q be a rational number such that the prime factorization of q, the denominator, is in the form of 2 power of n into 5 power of n, where n and m are non-negative, that means they can be 0 and positive, then x has a decimal expansion which terminates after k places, where k is larger of m and n. How do we prove this? For example, we take 51 by 64. Okay. How do you write, or what is the prime factorization of 51 by 64? 51 is 17 3s are, right? 64 is 2 power of 6. Now, in this case, what is the power of m here? Assume a hypothetical n. What is the power of m here? 6, right? What is the power of n here? 0. And here m is greater than n. So, what will be k here? 6. This means that the decimal expansion of 51 by 64 will stop after 6 places. Check yourself in the calculator. This will be right. Let's try one more example now. Okay. After how many places the decimal expansion of 8 by 32 goes? How do you write 8? 2 power of 3. And how do you write 32? 2 power of 5. So after cancelling, what do you get? You get 1, 2 square. Right. Here k is what? 2. Because if you assume that 5 power of 0, 2 is greater than 0. So k is 2. Does the decimal expansion of 8 by 32 ends after 2 digits? Definitely. See, 8 by 32 is 1 by 4. 1 by 4 is 0.25. It ends after 2 digits. So this is how you will determine whether after how many places does the decimal expansion of a rational number which has a denominator in the form of 2 power of n and 5 power of m will end. So far we have seen how to determine whether a number is terminating or not. How do you know? Because the denominator should be in the form of 2 power of n and 5 power of m. So if it is in the form of that, then we know for a fact that it is terminating decimal. But what is the other definition of rational number? Rational number can also be considered as that number which has the decimal expansion of non-terminating and recurring. Here recurring means repeating, that is there is a sequence of digits that occur. For example, 1 by 7, 7 ones are 7, 3, 30, 7 fours are 28, again 2, 20, 7, how much? 7 2s are 14. Again we get here as 6, 0. 7 8s are 56. Again we get here as 4, 0. 7 5s are 35. Again we get 5, 0. 7 7s are 49. Again we get 1, 0. 7 1s are 7. Again we get 3, again 0, so 4. If you observe the trend here, the decimal expansion of 1 by 7 can be written as 0.142857 bar. Because it repeats, it stops here and it repeats again. So it is not terminating, but it's recurring. There is a pattern in the sequence. Right. For such numbers as this, here if you see the denominator, it is not in the form of 2 power of m into 5 power of n. Again, for example, if we say 100 by 81, what is the prime factorization of this? You get 2 square into 5 square is 100 and 81 is 3 power of 4. Right. So if you see this, is the denominator in the form of 2 power of m into 5 power of n? No. It is simply 3 power of 4. Right. So in this case, can you say that a number is terminating? No. So whenever there is the decimal the denominator is not in the form of 2 power of n and 5 power of n, then x has the decimal expansion which is non-terminating recurring, that is this. These two are solid cases of non-terminating and recurring. Let's see one more thing, 100 by 64. Okay, so what is 100 by 64? 2 square into 5 square. How do you write a 64? 2 power of 6. This is terminating because the decimal, if you cancel this also, the denominator is in the form of 2 power of 4. That is, it's in the form of 2 power of 4 into 5 power of 0. So it is still terminating. If you see this, you will be able to get to its shortest form and terminate the decimal. That is, here what happens? 2 power of 25 by 16. So if you divide 25 by 16, we get 19, 16, 5 are 80, 100, 1.5, 100, 16, 6 are 96, we get 4. After how many decimals it should end? 4 based on the second theorem. 40, 16 2s are 32 and then 8, 5. Is it ending at 4? Yes, see. 1.5625 is 25 by 16. So it is stopping there, it's terminating. So in this case, have at least 5 or 2 in the denominator, then we'll get it as terminating. If we have, suppose say, into 3, that is nothing but 100 by 64 3s is how much? 12, 192. Then it won't work. It will not be terminating because 2 square into 5 square, but what is this? 2 power of 4 into 3, right? 3 is there here. It's not in the form of 2 power of m into 5 power of n. That means the denominator should have only the combination of these two prime factors. That here we have 3 here. So in that case, this is out of the boundaries of 2 and 5. In that case, you can say that this number is non-terminating but recurring. Okay, this is what this theorem is saying. This is how you can prove whether the decimal expansion of rational numbers are terminating or non-terminating but recurring. I hope you understood the video. If you like my video, I request you to please like, share and subscribe to my channel and ring the bell notification down below so that you will never miss an update from me. I hope you understood the concept so far, and if in case of any questions, please leave a comment down below. So I will see you all in my next video. Until then, I hope you have a safe, wonderful week. Bye.